All right, for today's video, we are going to talk about some properties of logarithms. So as I'm going through these, looking and I'm saying there are several basic logarithm properties we're going to look at. There are some things that just kind of happen, but and they fall out. That the basic ones that I'm going to talk to you about are going to tie back to our exponent rules. So if you remember that a logarithm is another way of writing an exponent. Logarithm or another way of writing exponents. An exponent. And if you go back and you think about what we were talking about, where we said log base answer equals exponent. Okay, this is a direct manipulation from the fact that when we have something that's written in exponential form, it looks like base to the exponent equals my answer. So this could be, I don't know, 3 squared, the exponent is a 2, equals the answer. So let me go with that since I just said it. 3 squared equals 9. We know that one. Well, if we're rearranging this guy around to make it look like a logarithm, then it's log. The base here was a 3 of the answer, which we said was the 9, equals the exponent, which we said was a 2. Okay, so if you can get it into your head somewhere, get it back on your paperwork or whatever, log base answer equals exponent, then you can move pretty fluidly between the exponential form of the stuff and the logarithm form of stuff. So what I mean by some things just kind of fall out is that whenever you start looking at logs and stuff like that, you have some basic rules that kind of fall out. So for instance, log with any base of 1 equals 0. Okay. Well, that falls out because this comes from the exponential. It would have been a to the 0 equals 1. Well, we know any base, a stands for any base here. Any base raised to the 0 power equals a 1, because remember we worked on that when we looked at exponents. So for instance, it was, we might have had something like x to the 5th divided by x to the 5th. Well, we used our exponent rule for division, which was x to the 5 minus 5, which gave me x to the 0. But we knew x to the 5th over x to the 5th, that will reduce and give me a 1. So all of that is equal to a 1, right? So we can kind of skip those in between exponent steps and say, hey, anything you've got raised to a 0 equals 1. So on the logarithm side of things, whenever we start looking at logs, this is the equivalency for that rule, that exponent rule. So log base a of 1 equals 0. So that just kind of falls out. Okay, and other stuff is just going to fall out too. So there's a rule that says log base a of a equals 1. Okay, and in my head I'm thinking, well, where did that guy come from? Well, he came from, rearrange this into an exponential. A is the base, log base answer, this is going to be on the other side, equals exponent. So a to the first equals a. Well, yeah, of course that does. A to the first equals a, and the a again stands for any base. So anything raised to the first power, you just get that thing, right? X to the first power, I just get an X. So again, these are kind of, they're little rules or properties that fall out. And I think that they just kind of naturally flow from those exponent rules that we've had before. So hopefully you can see them and they're good. So some of them look a little complicated. So I want to throw some of those out there for us. So this one is A is my base raised to log base A of m equals m. Okay, and that's a weird one. It looks really kind of weird, but if you kind of rearrange these things, this is an exponential. This will become log base A of the answer, m, equals log base A, because that's my exponent, right? So base, this is my exponent, this is my answer. So again, this is just kind of a weird way of saying, yeah, if I rearrange this into an exponential or into a log base A, then yeah, I'd get the same thing. So that one kind of looks weird to me. I don't normally use this one except to say that basically, if you have A in the base and you have log of A up in the exponent, those two are basically going to just drop each other out. Like it's almost like this is an exponential, this is a logarithm. They're kind of undoing each other and the m just drops out basically. Okay, so that's a weird one, but it comes in. And then the last one that I saw in your book that may pop up in a homework or something that you might have to use is log base A of A to the R equals R. Okay. And I'm going to use a little property that's we're going to find. This one that we're going to find in a second is actually going to be very useful for us as we move forward. But basically, the rule is going to say, hey, remember when we did x to the third and we squared it? Okay, so it was an exponent raised to an exponent. What did we do? We multiplied those exponents together, right? X to the third times 2. So we got x to the 6th, right? Okay, we just multiplied our exponents. Okay, well, if I think of this log base A of A as if it was an exponent, and it's being raised to an exponent, if you got an exponent to an exponent, you can multiply those, right? So it's basically going to end up that I can pull this exponent down in the front and multiply these guys. Okay, so this is going to give me log base A of A times R equals R. But hang on a second, we just found log base A of A. It's up here. Log base A of A equals 1. So that's just a 1. So sure enough, that's just a 1. R equals R. Of course it does, right? So these guys, whenever I have, again, this was the original. Let me rewrite it. Log base A of A to the R equals R. This is the property that was in the book. Okay. And again, it just kind of seems like, hey, when I've got a log base A and the base here is an A, those will go away, the R will drop out. Now it doesn't just drop out, it actually moves to the front, like I said a minute ago, and it'll end up being multiplied by this one guy. But it ends up looking like the same thing. Hey, you know, this is just gonna kind of go away and I get whatever was the exponent raised to the exponent, right? So those are just kind of some unusual little properties that are out there. So if you know them and you see them, maybe they'll help you move through some stuff faster. They kind of relate back to those exponent rules that we've already talked about. So those I'm not so worried about. The ones I want to work on are these right here that are about log base A of m times n is what it says. So the log base A of m times n, and I'll give us an example in a second. The rule says that if you've got two things multiplied, okay, with the same logarithm base, then I can split this up into addition. Log base A of m plus log base A of n, okay? So, and in my head, this comes from the fact that I had two things that are exponents, x squared times x to the third, for instance, okay? So this thing has an exponent and they're multiplied, times this thing has an exponent being multiplied. So there's like times right in here, right? Okay, if you remember our exponent rule, what did we do? We added the exponents, right? 2 plus 3. So we ended up with x plus x to the 5th. So that was my exponent rule, was add. Okay, when you're multiplying two things with the same base, okay? And that's how I think of this whenever I'm looking at logarithms. I've got this logarithm with this base, and inside of it, I'm multiplying two things together, okay? So it's like I'm multiplying two things with the same base. So when I split these up to be able to add them, or I could go backwards, but whenever I split these up, it's going to be log base A of the first guy plus log base A of the second guy. Okay, so basically you're going to have to start doing some stuff where you're like, oh, where are some really great examples of this, basically? Well, the examples of these come from the fact that we might have something like this. Log base A of, let's just skip the A for right now. Let's just make it a base 10. That's the common log, right? Because we normally work in base 10 numbers. So log base 10 of, we're going to say 3 times 7. Or you would have been looking at this as log of 21, right? Okay. Now you're going to eventually get to where we're punching some of this stuff on our calculator. And yes, we can do log of 21 on our calculator. And hopefully we get the same answer that we'll get whenever we do this splitting them up, because we're going to use these lovely properties. But I'm not going for an exact answer right now, or even a decimal approximation. Like I think log of 21 is something like 1.39. We're not going to use the calculator right now. We'll introduce that later. But instead, we're going to just use this property and see how we can split it up. So log, this would be, if I split this up, these are multiplied, it would be log base 10 of 3 plus log base 10 of 7. So basically anything you can multiply together. What if I had something like, let's see how we split up this one, the log of 16. Okay, so hopefully you can see lots of ways that you can split this one up. Like you could do, this is the log of 2 times 8, right? Which would be the log of 2 plus the log of 8. But somebody else might see, oh, wait a minute, I see that this is the log of 4 times 4, which would be the log of 4 plus the log of 4. So I'm just taking the two things that are multiplying and I'm splitting it up, and I'm writing two separate logarithms with the same base, and I'm just adding them together, right? So hopefully you can see, oh, okay, that would be two different ways I could write it. It could also be log of 1 times 16. So that would be log of 1 plus the log of 16. The trick here is whenever we go to do these later and we are simplifying these or putting in decimal approximations, those better all be equivalent, right? So if you're punching on your calculator, you better be able to punch log of 16. And then that should be the same number as if you did log of 4 plus log of 4. Okay, so that's the way that that falls out for us. All right, going the other way, what if it was something like you saw, I've got the log of 7 plus the log of 4. Okay, and what if your direction said something like cram this together into make one single logarithm? So we know these are added. We know that the addition comes from when we were multiplying like bases with different exponents. So it's added now. I want to cram it back together and make it a single logarithm. That would be log of 7 times 4, or log of 28. And no matter how I do this, these all better come out the same if I punch them on my calculator. Okay, so that's the first property. That goes with multiplication inside of a logarithm. So let me write that. Multiply inside a logarithm. Remember that a logarithm is just a different way of writing an exponent. Okay. So the next one that we did was, what if we're dividing inside a logarithm? Well, let's take a second and go think about what happens when we're dividing exponents. So x to the 8th, for instance, divide by x to the 3rd. Okay, same base. So that's the important part. These logarithms all need to have the same base. If they do, then I can use these rules. So the rule was this is going to equal x to the 8 minus 3, right? Take the top exponent and subtract the bottom exponent. So this is going to become x to the 5th. That was the exponent rule that went with this. So it was subtract, right? When you got division going on with the same base, different exponents, even same exponents, you just subtract, right? So the rule here is going to be log base A. I'm going to have m divided by n. So there is division going on and they have the same base, okay? And I'll be able to split that guy out. But instead of, just like I did up here, but instead of adding, like I did with the multiplication, I'm going to subtract. So log base A of the m guy minus log base A of the n guy. Okay, so, and they call this, a lot of times they'll call it a simplified form because I'm no longer got that division going on. It actually, to me, looks more complicated because I've got all this other stuff going on. Log base A minus log base A, but that is the rule. So that guy, we have this guy up here from the multiplication, that guy. There's going to be 3 big ones that we use a lot as we go forward. So those are the 3 I'm going to hit on today. So this one, let's see if we got some of this stuff going on. What if it was, again, I'm going to just revert to the common base of log base 10 because it could be any base, but we're just going to do the ones that we're used to seeing. So like base 10 is one of our go-tos. So what if it was log base 10 of, let's say, 18 over 4. Okay, this is not going to reduce very nicely for me. So it's not one where I would go ahead, that would be 9 over 2, right? And that's not going to divide evenly. So it's not one that I would go ahead and simplify. But we'll see in a second, I can take things that are actually nice and pretty, and I can make them into division problems if I need to. So this would be what? You always start on the top. Log base 10 of the 18 minus log base 10 of the 4. Okay, so the top minus the bottom is the way we always do it. So that is a deconstruction of this logarithm. We've split it up so that it's 2 separate logs being subtracted. Okay, so that's what that would look like. Let's try the other one. What if I was just like, oh man, log of 18? Okay, and I didn't know that, but I knew some other stuff. Well, this could be the log of, say, 36 over 2. Isn't 36 over 2 still 18? Yeah, so that could substitute out, right? So if I've got that, then now I could rearrange it. So I don't have to do that. It's just one of the many ways these can be rewritten. So lots of equivalent forms going on with this stuff. So log of the top guy is 36 minus log of the bottom guy is a 2. Okay, that's what that looks like. Okay, and then I've got one where you can rearrange it the other direction, of course. So for instance, if they give it to me as a subtraction of 2 different logs, but they have the same base, then I can rearrange it so that it is one problem. So this one looks like they just threw in a base 2 just to mix it up a little bit. Log base 2 of, and of course, things have to start getting complicated. So they give me some variables, x squared plus 1 minus the log base 2 of 5. Okay. I don't care that there's variables or anything like that. Again, I'm just comparing these 2 logarithms. They have the same base, log base 2. So as long as they have the same base, then I can use that. So I'm going to shove them back together. And the rule said, whenever it started, like reading this backwards, if I start with subtraction and I go the other direction, then this is going to become a single logarithm with the first guy divided by the second guy. So this is going to become log base 2 of, the first guy is x squared plus 1 over, I already wrote my fraction sign, over the second guy is a 5. So remembering that whenever I cram them back together, it's just going to be one logarithm. So log base 2 of something. And a lot of times in the directions for those homework questions, they'll say, write these as a single log. That means you're either add, subtracting, or multiplying. So you got to put them all back together. All right. So that's the second rule. And then the third rule, and these are the three big properties that we're going to use, is the one we actually kind of looked at it earlier. Log base A of m, so this is my exponent, raised to an r, so that's an exponent to an exponent, is equal to, and we're going to use what we said a little bit ago. Pull this r down, multiply them. R times log base A of m. And we actually end up using this one a lot. Okay. So again, what did I say earlier? This stems away from that power to a power rule. X third squared is, this is an exponent being raised to an exponent. Well, here my logarithm is an exponent and it's being raised to an exponent. So the rule was you multiply the exponents, right? Okay, so this was x to the 3 times 2 or x to the 6th. That's the exponent rule that we're utilizing here. Let me scoot this up. That's the exponent rule that we're utilizing here. So it's going to look just a tiny bit different. Is remember, log base A of m represents, oh my goodness, I can't write, represents an exponent So this is exponent to an exponent. So we will multiply. This leads me to multiply. So that's the property we're trying to use from the exponent rules. So this is going to be end up looking like, take whatever that guy is up in the air and write him out in front. Exponent times whatever the exponent was, the logarithm originally was. That's what this is. So that's what they're doing here. Take that exponent, write it out in front, and then we're going to multiply. Okay. So that is the use of that particular exponent rule. So what's that look like? Okay. Well, it looks like if I had something like, log, I'm going to go base 10 again, log base 10 of 7 squared. Okay. There we are with that. Well, guess what? This is an exponent. The logarithm is an exponent and it's being raised to an exponent. So I can rearrange that by multiplying. So pull this guy down in front, 2 times log base 10 of 7. There you go. And then I can do stuff with that, whatever I need to do. Okay. So they end up giving me several examples of these, and they're going to make them harder and harder. So I'm going to give you, a more complicated one in just a second. But just remember that, okay, you're going to be doing stuff like 2/3 log of 8. And it might say, write this as a single exponent. Okay, so, or a single logarithm, sorry. In this case, it's got it backwards, right? This number is out in front. So I need to raise it. So log of 8 to the 2/3. And you can even use your exponent rule to say, hang on a second, I know that this is that flower power deal, right? So you could even say this is the cubed root of, because the roots are on bottom, log base 8 squared, right? So the 2 would be the power or the flower or the exponent in this case. All right. So there is some fraction stuff out there too. So don't forget about that fraction stuff. All right. So what if I had something like this and it just said solve? Here's an example. Solve. Y equals log base 2 of 10, of 7. Okay. And we're just like, I don't know how to deal with log base 2 yet. We'll get there where we're playing with it in the calculator and stuff. But in the meantime, we can just rearrange this into an exponential equation, right? So this is a logarithm, but I know that this comes from, this is equivalent to the base, which was the 2, raised to an exponent, which is the y, is equal to the 7, which was my answer, right? Log base answer, this is my answer, equals exponent. So it's kind of backwards, but that's what it means. So 2 to the y equals 7, okay? Well, then I can do stuff like take the log of both sides, okay? So, and a lot of times when we do that, we do the natural log. So ln is the natural log. ln of 2 to the y equals ln of 7. I can take the log of both sides as long as I do it to both sides, right? And so then you say, oh, look at this, but now I've got this y guy up here. He can come down in front. Y times ln of 2 equals ln of 7. And now I can completely solve for the y guy by dividing by ln of 2. Y equals ln of 7 over ln of 2. Okay. So just some ways to rearrange stuff and make it look different and use some of these properties. We will find out how to punch that stuff on our calculators, just not right now. Let me give you one more, a little bit more complicated example, and then I think I'm going to be just about out of time. So I might give you one to work on your own. So hold on. All right, so here we go. Here's another example. It looks like the log of 4, I'm sorry, log base 4 of x plus the log base 4 of x minus 3 equals 1. So again, we're getting some variables in here, but we can handle it. It'll be all right. So what I want to say is, where did this plus thing come from? That must have been, these are the same bases, log base 4, log base 4. That must have been multiplication, right? So I can push this stuff back together. Log base 4 of, this would be x times x minus 3. So I'm going in reverse, right? If I want to, I had addition, I'm going to cram these together, one single logarithm, and then whatever was here, the x, is being multiplied by whatever is there. So that is when you're multiplying exponents with like bases, you keep the base, which we did, and multiply the exponents, which we did, okay? All that equals a 1. All right, but then I know, hang on a second, this stuff right here is going to be x times, I can simplify it, right? Log base 4 of all of this stuff is x times x is x squared, and x times 3 is minus 3x. Okay, so that's all that stuff in there, and all that still equals to a 1. And then I can rearrange this yet again. So this is all that logarithm stuff crammed into one logarithm. Okay, great. We got it pushed back together. We multiplied it. We got that. But now I know this is log base answer equals exponent, right? Okay, so I can rearrange this as, here's my base, 4 equals exponent, that's my 1. And this is log base answer. So this all this stuff goes to the other side. Oops, sorry, x squared minus 3x. All right. Well, now I've managed to get rid of all that logarithm stuff, right? And I just have a nice, pretty quadratic equation, which we like those. So let me rearrange this. I'm going to subtract 4 from both sides to get rid of that. 0 equals x squared minus 3x minus 4. And now I just have a pretty quadratic equation, and y'all can solve that for sure, right? So it looks to me like it's going to be x minus 4 and x plus 1. Again, if you can't factor that guy pretty quickly, then start working on your factoring skills. Make sure you can do it. Negative 4x plus 1x gives me the negative 3x minus 4. And then this guy we would just solve like normal. X minus 4 equals 0, or x plus 1 equals 0. X equals 4, x equals negative 1. There you go. All right, so we got all that stuff going on, and it basically used all those logarithm stuff and then came down and used properties that I definitely know how to solve this quadratic, right? So I'm going to give you one, and then I'm going to pause it and solve it, and you can pause and play with yours, and hopefully you'll be able to work it out and get to where I am at the same time. So my example is 1/2 log base 3 of x is equal to 2 log base 3 of 2. So hopefully you can use some of your logarithm properties like this out here, this 1/2. I know that that means it was an exponent to begin with, right? So I'm multiplying them. So I'm going to move that to the top. And I'm going to move this 2 on the other one to the top. So rearrange that stuff and see if you can solve it. Pause. I'm going to come right back with my work and my solution. I'm just trying not to use too much time on video. So here we go. Okay, so I'm hoping that you've at least gotten to the spot where you have the x to the 1/2 and you have the 2 squared, which is going to give me a 4. So I went ahead and rearranged that. And then I realized there's probably about 4 different routes you can go at this point. But I see I've got a log base 3 equal to a log base 3. So what I'm going to do is I'm going to do 3 raised to those exponents on both of those, because I know that a base to a power with the 3, the same base, those are going to go away. Remember that little rule we used just a little bit earlier ago? So x to the 1/2 equals a 4. That's where I am. There's other ways you can do that. You could rearrange it so it's a subtraction problem. You could do all kinds of stuff here, but I think this is the fastest route for me because it automatically drops me down into, I've got x to the 1/2 equals to a 4. So I'm looking at this guy going, okay, the 1/2, that's the same as a square root, right? So this is like square root of x equals 4 is what they're telling me. So I can look to see whose square root gives me a 4, or I can just square both sides. The square and the square root will go away. X equals 16. All right. So there's a lot going on with these things and I'm way out of time. So go do some of the homework. This is, I think, 4.3 in your homework, and see how that falls out and see if you can do them on your own or not. All right, that's it. Thanks. Have a good week.